Okay, welcome everyone to the deep dive. It seems like a lot of you out there are really keen to get a solid grasp on how refrigeration systems work on ships, and we've gone ahead and gathered a pretty impressive stack of materials to dig into.
Yeah, we've got excerpts and diagrams covering pretty much everything.
The basic principles of refrigeration and AC, the specific ways those are designed for use on ships, all the crucial components, the different types of refrigerants, how to maintain these systems, and even some of the finer points.
Things like superheat and subcooling.
Exactly, and how they control capacity too. So our aim in this deep dive is to pull out the really essential knowledge from all of this so you walk away with a clear understanding of how these systems function and why they're so vital out there on the open ocean.
Absolutely. It's amazing how much we take them for granted.
It really is. So I guess a natural place to start would be with the fundamental need for refrigeration on ships.
Right. And it's obviously about keeping food fresh for the crew.
Of course, provisions.
But, that's just the beginning.
The tip of the iceberg, literally.
Aha, exactly. We're talking about preserving massive amounts of cargo from perishable foods to temperature-sensitive chemicals to the transportation of liquefied gases, which wouldn't even be possible without refrigeration.
Right, you'd have no way to transport them.
Without reliable cooling, the risk of spoilage is huge, whether it's from microbial growth, oxidation, fermentation, or just plain drying out.
Yeah, think about the economic impact if all of that stuff was just spoiling left and right.
It would be disastrous.
And as you say, it's not just about specialized vessels either.
Nope.
Every single ship out there relies on refrigeration just for the crew's provisions.
Absolutely.
Then you've got your dedicated reefer ships carrying refrigerated cargo.
Right.
And then those massive gas carriers that need to maintain like cryogenic temperatures to keep their loads in a liquid state.
It's mind-boggling, the scale of it.
Really is. It's this universal requirement across the maritime industry.
Completely. And the funny thing is, the basic principle behind any refrigeration system, whether it's on a ship or in your kitchen, is pretty straightforward.
Okay, yeah, how would you summarize it?
Well, you're basically taking heat from a place where it's not wanted, like the cold space you're trying to maintain,
Okay.
and you're moving it to a place where it doesn't really matter, a warmer environment.
So moving it out of the way.
Exactly. And the key player in all this is the refrigerant.
The refrigerant.
It's a substance that can absorb and release heat super efficiently as it cycles through the system.
Makes sense. Now, our sources mention two main types of refrigeration systems used on ships, vapor compression and vapor absorption. Can you walk us through those?
Sure. So both of them, at the end of the day, are about removing heat,
Okay.
but they go about it in different ways. Vapor compression systems use a mechanical compressor to pump and compress the refrigerant gas.
Okay.
Vapor absorption systems, on the other hand, use a thermal process.
Thermal.
Yeah, it involves a heat source, an absorbent, and a generator to drive the cycle. But the interesting thing is, from what I gathered, the vast majority of ships use vapor compression.
Okay.
Much more common.
So for this deep dive, we'll focus on the vapor compression type.
Sounds good.
Now, one of the things that really struck me in the material was the idea that, cold isn't actually a thing in itself,
Oh, yeah.
but rather the absence of heat.
That's a good one.
Can you explain that a bit more?
Yeah, it's kind of a mind bender. We talk about things being cold, right?
Right.
But really what we're describing is just the absence of a greater amount of heat energy compared to something else.
Okay.
Like everything has some heat.
Even things that feel cold to us.
Even ice.
Huh.
It has heat energy, just less of it.
So it's all relative.
Exactly.
So refrigeration isn't about creating a coldness, it's about removing heat.
Absolutely. It's about taking the heat that's already there and moving it somewhere else.
Okay, makes sense. Our sources also talk about the different ways heat can move around: radiation, conduction, and convection. How do those play into how refrigeration systems work?
Those are the three ways heat is transferred. So conduction is the simplest.
Okay.
It's heat transfer through direct contact. Like if you touch a hot engine part, you feel that heat because of conduction.
Okay.
Then you've got radiation.
Radiation, yeah.
That's heat transferred through electromagnetic waves.
Like the sun.
Exactly. That warmth you feel from the sun, that's radiation.
Okay.
And then the last one is convection.
Convection.
Convection is heat transfer through the movement of fluids, like liquids or gases.
Okay.
Think about air circulating in a room.
Okay.
That's how heat is distributed around.
Makes sense.
Now, refrigeration systems essentially harness these natural processes.
Oh, interesting.
Yeah, they expose the space or object you want to cool to something that's at a lower temperature.
Okay.
And that's your evaporator in the refrigeration system.
The evaporator.
And that encourages the heat to naturally flow from the warmer area to that cooler refrigerant.
Okay, so it's like creating a path for the heat to escape.
Exactly. And then the system takes that absorbed heat and dumps it somewhere else outside of the space you're trying to cool.
That's clever. Now, I also noticed the term ton of refrigeration in the material, and I have to admit that sounds a bit old-fashioned.
Yeah, it does have historical roots going back to the ice-making industry.
Okay, so how did that term come about?
Well, back in the day, they needed a way to measure the cooling power of their systems.
Right.
So they came up with this benchmark. They defined 1 ton of refrigeration as the amount of heat needed to freeze 1 ton, that's 2,000 pounds of water, at 0 degrees Celsius into ice, also at 0 degrees Celsius, over a 24-hour period.
Wow, so it's literally based on the amount of ice you could produce.
Precisely.
Interesting. And so in today's terms, what does that actually translate to?
Well, 1 ton of refrigeration is equivalent to removing heat at a rate of 12,000 BTUs per hour, or about 3.5 kilowatts.
BTU.
Right, British thermal units.
Right, those always confuse me. Remind me what those are again?
A BTU is simply the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit.
Okay, that helps, but it's important to remember that adding heat doesn't always lead to a temperature increase, right?
You got it. Think about boiling water.
Okay.
When water reaches 212 degrees Fahrenheit, adding more heat doesn't make it hotter.
Right.
Instead, it goes towards changing its state from liquid to steam.
Okay.
And that takes a lot of heat, by the way. It's called the latent heat of vaporization.
Latent heat.
Yeah. For water, it's a whopping 970 BTUs per pound.
Wow, that's a lot of energy just to change the state.
Exactly. And this whole concept of latent heat, where heat drives a change in state without changing the temperature, is really at the heart of how the refrigeration cycle works.
Okay, so changing state is key.
It's crucial. And we also know that the boiling point of any liquid, including our refrigerants, is directly tied to pressure.
Pressure, right.
If you increase the pressure, the boiling point goes up. Decrease the pressure, it goes down.
Makes sense.
This relationship between pressure and boiling point is the engine that drives the whole vapor compression cycle.
So let's talk about the vapor compression cycle. Our sources say it's the most common system on ships. What are the main parts of it?
Well, the cycle has 4 main components.
Okay.
You've got the compressor, the condenser, the evaporator, and the metering device, which is usually an expansion valve.
Okay, 4 main components.
And the whole cycle has a high-pressure side and a low-pressure side.
So starting with the compressor.
The compressor is like the heart of the system.
Okay.
It takes in the low-pressure, low-temperature refrigerant vapor from the evaporator,
Okay.
and it squeezes it, compresses it, which significantly increases both its pressure and temperature.
So you've got hot, high-pressure gas now.
Exactly, and that flows into the condenser.
And the condenser gets rid of the heat, right?
You got it. The condenser's like a heat exchanger. And on ships, it's usually cooled by seawater.
So you're basically transferring heat from the refrigerant to the seawater.
Precisely.
Okay.
As that hot, high-pressure gas flows through the condenser, it loses heat to the cooler seawater.
Okay.
And that causes the refrigerant to condense.
To change state.
Yeah, it goes from a gas back into a high-pressure liquid.
Okay, so we've gone from low-pressure gas to high-pressure gas, and now to high-pressure liquid. Where do we go from there?
Now it goes to the metering device.
That's the expansion valves, usually.
Right, in most cases.
Okay.
This device has a tiny little opening that creates a bottleneck.
A bottleneck.
Yeah, it restricts the flow of that high-pressure liquid.
Okay, so what happens?
This restriction causes a big pressure drop.
Okay.
And here's a key point. When the pressure of a liquid drops, its boiling point also goes down.
Oh, so now we have a low-pressure liquid that's ready to boil at a much lower temperature.
Exactly, and that's where the evaporator comes in.
Evaporator.
Right.
Okay, so walk me through that.
So the evaporator is another heat exchanger, but this one is located in the space you actually want to cool.
Like the cargo hold?
Right, or a room for provisions. Because that refrigerant coming in is now a low-pressure liquid with a very low boiling point. It easily absorbs heat from anything around it.
Okay.
From the air, from the cargo, whatever. And as it soaks up that heat, it starts to boil.
Okay.
And changes back into a low-pressure gas.
Okay.
This evaporation, this change of state, is what actually does the cooling.
That makes sense. So what happens to that gas?
Well, that low-pressure gas is then sucked back into the compressor, and the whole cycle starts all over again.
It's a loop.
Yeah, this continuous loop of heat removal and relocation.
Fascinating. So the refrigerant just keeps circulating, grabbing heat in the evaporator and dumping it out in the condenser.
Exactly. And the whole thing is powered by this clever manipulation of pressure and the properties of the refrigerant.
Pretty ingenious. Now, the sources also talk about something called saturation.
Uh-huh.
What does that mean when we talk about refrigerants?
Saturation is all about phase changes.
Phase changes.
Yeah, so it's the point where a substance is changing from a liquid to a vapor, or from a vapor back to a liquid.
Like the boiling and condensing we were just talking about.
Exactly. And for any given pressure, there's a specific temperature at which this phase change happens.
Okay.
That's called the saturation temperature, or a boiling point.
Okay.
So if you've got a liquid at its saturation temperature for a given pressure, we call that a saturated liquid.
Saturated liquid.
And similarly, if you've got a vapor at its saturation temperature, it's a saturated vapor.
Okay.
And if the pressure stays constant, which we call an isobaric process,
Isobaric, all right.
adding heat to a saturated liquid will make it boil.
Okay.
And taking away heat from a saturated vapor will make it condense.
So in the condenser, we're basically trying to desaturate the vapor, right?
Yeah, you could think of it that way. You want to push it out of that saturated vapor state and into a saturated liquid state.
And in the evaporator, you're doing the opposite.
Exactly.
So it's all about controlling that balance.
Right.
Now, we also came across the terms sensible heat and latent heat. I think I touched on latent heat earlier.
With the boiler water, yeah.
But can you explain the fundamental difference between these two types of heat?
Sure. So sensible heat is the kind of heat we're most familiar with.
Okay.
It's the heat that you can feel, that you can measure with a thermometer.
Okay.
When you add sensible heat to something, its temperature goes up.
Okay.
And when you take sensible heat away, its temperature goes down.
Makes sense.
Latent heat, on the other hand, is a bit more subtle.
Okay.
Latent heat is the heat that goes into changing the state of a substance without changing its temperature.
So like when ice melts into water.
Exactly. That's called the latent heat of fusion.
Latent heat of fusion.
And when water boils into steam, that's the latent heat of vaporization.
Okay, so latent heat is about breaking or forming bonds between molecules.
Precisely. And the energy involved in that doesn't show up as a temperature change.
Interesting. Now let's move on to some other important concepts, superheat and subcooling.
All right?
What exactly is superheat?
Well, superheat is what happens when a vapor is heated above its saturation temperature.
Okay.
But for superheating to occur, all of the liquid has to have boiled off first.
So it's only after everything is turned to vapor.
Exactly. Imagine you have a pot of water on the stove and it's boiling.
Okay.
At that point, the water vapor is at its saturation temperature, which is 100 degrees Celsius at sea level.
Okay.
Now, if you keep adding heat, the temperature of that steam will start to rise above 100 degrees.
Okay.
That's superheat. It's how much hotter the vapor is than its boiling point at that pressure.
And so in a refrigeration system, where do we measure superheat?
We typically measure it at the outlet of the evaporator.
Like evaporator.
Right.
Okay.
That tells us how much the refrigerant vapor has been heated up after it's absorbed heat from the space we're trying to cool.
Okay.
And thermostatic expansion valves, which we'll talk about more later, are often set to maintain a certain amount of superheat to ensure that only vapor, not liquid, goes back to the compressor.
So superheat is like a safety margin
You could say that, yeah.
to protect the compressor.
Precisely. Now, subcooling, as you might guess, is sort of the opposite of superheat.
Okay, how so?
It happens when a liquid is cooled below its saturation temperature.
So if water boils at 100 degrees Celsius,
Uh-huh.
cooling it down to 90 degrees would mean it's subcooled by 10 degrees.
Exactly. And this subcooling typically happens in the condenser.
So superheat on the vapor side, subcooling on the liquid side.
That's the gist of it, yeah. And both of these play a role in how efficiently the system operates.
Got it. Now, the sources also mention critical temperature and critical pressure. What are those all about?
The critical temperature of a refrigerant is the highest temperature at which it can exist as a liquid, no matter how much pressure is applied.
Okay.
Above that temperature, it's always going to be a gas.
I see.
And the critical pressure is the pressure you need to apply to liquefy the refrigerant at its critical temperature.
Okay, so they go together.
Exactly.
And why are these important?
Well, typical refrigeration cycles work best when the refrigerant stays below its critical temperature,
Okay.
because the condensation process in the condenser is crucial for the cycle to work.
So these critical points set the limits.
Yeah, boundaries for efficient operation,
Okay. And then there are all these different types of pressure within the system.
right?
Vapor pressure, condensing pressure, evaporating pressure.
Yeah, those are important to understand.
So what's the deal with vapor pressure?
Vapor pressure is the pressure that a saturated liquid exerts at a given temperature.
Okay.
You find it wherever you have both liquid and vapor coexisting.
Like in the condenser and the evaporator?
Precisely. And the higher the vapor pressure, the higher the saturation temperature.
So they're linked.
Yeah, correctly.
Okay, and what about condensing pressure?
Condensing pressure is the pressure in which the refrigerant changes from a vapor to a liquid in the condenser.
Okay.
You can measure it anywhere between the compressor outlet and the inlet of the metering device.
Okay.
And then there's evaporating pressure.
Right.
That's the pressure where the refrigerant changes from a liquid to a vapor in the evaporator.
And you measure that.
between the outlet of the metering device and the compressor inlet.
Got it. So monitoring these pressures gives you a snapshot of what's happening inside the system?
Exactly. It tells you whether the phase changes are happening where they should be.
Makes sense. Now, how do we know how efficient a refrigeration system is? I saw the term coefficient of performance, or COP.
The COP is a really important measure of efficiency.
Okay.
It tells you how much cooling you're getting out compared to the energy you're putting in.
So a ratio.
Right. It's the ratio of the cooling capacity to the power consumption.
Okay.
And generally speaking, the lower the temperatures you need, the lower the COP will be.
So like a freezer would have a lower COP than, say, an air conditioner.
Exactly.
Makes sense. And is there a target COP we should aim for?
Well, it depends on the specific application and the system design, but generally, you want the COP to be as high as possible.
Higher is better.
Right. And it's interesting to note that the COP can actually be greater than 1.
Really? How's that possible?
It's because we're not creating cold, we're just moving heat around.
Oh, right.
So the energy we're using is to power that movement, not to generate the cold itself.
That's a really important point. Now, let's move on to refrigerants. The sources talk about a bunch of different types. What are the main categories?
So refrigerants have come a long way over the years.
Okay.
And a lot of the changes have been driven by concerns about the environment.
Right, the ozone layer, global warming, all that.
Exactly. Early on, they used chlorofluorocarbons, or CFCs.
CFCs.
Yeah. But those turned out to be really bad for the ozone layer.
Right, I remember hearing about that.
So they got phased out.
So what replaced them?
They move on to hydrochlorofluorocarbons, or HCFCs.
HCFCs.
Those were a bit better for the ozone layer, but they're still potent greenhouse gases.
So still not ideal.
No. And now the focus is on hydrofluorocarbons, or HFCs.
HFCs.
These don't damage the ozone layer, but some of them still contribute to global warming.
Oh, the search for the perfect refrigerant continues.
It does. And there's some other contenders out there, like natural refrigerants.
Natural refrigerants.
Yeah, things like carbon dioxide, ammonia, even propane.
Interesting.
Each has its own advantages and disadvantages.
So it's a balancing act.
Definitely. Safety, efficiency, environmental impact, all those things have to be considered.
Makes sense. Now, can you walk us through the main parts of a typical shipboard refrigeration system? What are the key pieces we'd find?
Sure. So you've got your compressor,
The compressor.
often a reciprocating type, which is pretty rugged and good for handling the demands on a ship.
Okay.
Then you have the condenser,
The condenser.
often a shell and tube type, cooled by seawater.
Seawater, right?
And it'll have a safety valve to vent off any pressure if things get too hot.
Safety first.
Absolutely.
What else?
Below the condenser, you usually have the receiver
The receiver. Okay.
that stores the cooled liquid refrigerant.
Okay.
And you can usually see the liquid level in there, so you know how much you have.
Makes sense.
Then you have the dryer.
Dryer.
Yeah. It's filled with a desiccant that removes any moisture from the refrigerant.
Moisture's bad.
Definitely. It can freeze up the expansion valve and cause corrosion.
Got it. What else?
Solenoid valves are used to control the flow of refrigerant to different compartments.
So you can cool different areas independently?
Exactly. And there's often a master solenoid, too.
What does that do?
That starts off the refrigerant flow to the evaporator if the compressor stops for any reason.
So it prevents flooding.
Yeah, prevents liquid from backing up into the evaporator.
Okay.
Then you have the expansion valve,
Expansion valve, right?
usually a thermostatic expansion valve, or TXV.
TXV. Okay.
That's a crucial part.
What does it do?
It precisely controls how much refrigerant goes into the evaporator
Okay.
to maintain the right temperature.
Okay, so it's like a regulator.
Exactly. And then there's the evaporator itself.
The
It's
evaporator.
another heat exchanger.
Okay.
And it's located in the space you're actually trying to cool.
Right, right.
It often has fans to circulate the cold air.
Okay.
And for systems that operate below freezing, like for frozen cargo,
Uh-huh.
you need a defrost system to keep the evaporator coils from icing up.
Right. Otherwise, they wouldn't work properly.
Exactly.
What else?
You'll have a control unit.
A control unit.
Yeah, that's the brains of the operation.
Okay.
It monitors the system and has safety features to shut things down if something goes wrong.
Okay.
Things like pressure switches, temperature sensors, that sort of thing.
Got it.
And then there's the oil separator.
Oil separator.
Yeah, that's a little device that removes oil from the refrigerant.
Oil.
The compressor needs oil for lubrication.
Okay.
But you don't want that oil circulating with the refrigerant because it reduces the efficiency.
Okay.
So the oil separator catches it and returns it to the compressor.
That's clever. What else is there?
Well, you have all the usual suspects, manual valves for isolating different parts of the system during maintenance,
Okay.
pressure gauges so you can see what's going on,
Okay.
sight glasses to check the refrigerant level,
Right.
thermostats to control the temperature,
Okay.
and filter dryers to remove any impurities.
Sounds like a lot of components.
It is.
And they all have to work together smoothly.
Precisely.
Now, you mentioned the thermostatic expansion valve, or TV, is really important.
Yeah, it's a crucial part.
Can we talk more about that?
Sure. So, as we said, it controls how much refrigerant flows into the evaporator,
Okay.
but it does this in a very clever way. It senses the temperature of the refrigerant vapor coming out of the evaporator,
Okay.
and it adjusts its opening to maintain a specific amount of superheat.
Superheat. Right.
Yeah, so that only vapor, not liquid, returns to the compressor.
Okay.
And it does this automatically.
How does it know how much to open or close?
Well, it has a temperature sensing bulb
Okay.
and a diaphragm that's connected to a spring.
Okay.
The pressure in the bulb increases with the temperature of the vapor,
Okay.
and that pressure pushes against the diaphragm, trying to open the valve.
Okay.
But there's also pressure from the evaporator and pressure from the spring that are trying to close the valve.
So it's like a balancing act.
Precisely. The valve finds its equilibrium based on those competing pressures.
That's really neat. So if the superheat increases, the valve opens wider,
Right.
and if it decreases, it closes a bit.
Exactly. And there are two main types of TVs: internally equalized and externally equalized.
What's the difference?
Internally equalized valve sense the evaporator pressure at the inlet of the valve,
Okay.
while externally equalized valves sense it at the outlet of the evaporator.
And why the difference?
Well, externally equalized valves are used when there's a big pressure drop across the evaporator coil, or when you have refrigerant distributors.
Okay.
It just makes them work more accurately.
Makes sense. Now, even with the best design, things can still go wrong.
Absolutely.
What are some of the common faults we might encounter in these systems?
Lots of things.
Give me some examples.
One common problem is air getting into the system.
Air. How does that happen?
It can happen during maintenance when you're charging the system with refrigerant,
Okay.
or if there's a leak on the low pressure side.
Okay.
And what happens is air doesn't condense like the refrigerant does.
So it messes up the cycle.
Exactly. You might notice the compressor overheating, high discharge pressure, or just poor cooling,
Okay.
and you might see bubbles in the sight glass.
The sight glass.
Right, that little window where you can see the liquid refrigerant.
Got it. So how do you fix that?
Well, you have to purge the air out of the system.
How do you do that?
Usually, you run the system and vent the non-condensables from the highest point, which is usually the condenser.
Okay.
Another common problem is moisture.
Moisture in the system.
Yep, water can get in, often with air,
Okay.
and that can cause all sorts of problems.
Like what?
It can freeze in the expansion valve, block the flow of refrigerant, and cause corrosion.
So how do you get rid of moisture?
Well, there are dryers in the system to absorb moisture.
Right, you mentioned those.
Sometimes you just need to replace the dryer cartridge,
Okay.
but if there's a lot of moisture, you might have to evacuate the whole system with a vacuum pump.
Wow, that sounds serious.
It can be, yeah. Then there's overcharging and undercharging.
Overcharging.
Undercharging, yeah. Overcharging is when you put too much refrigerant into the system,
Okay.
and undercharging is when there's not enough.
And those are problems.
They can be. Overcharging can lead to high pressures, reduce cooling capacity, and can even damage the compressor.
And undercharging.
Undercharging can cause the compressor to run too hot, low pressures, and again, poor cooling.
So getting the charge just right is important.
Absolutely. It's a Goldilocks situation. Not too much, not too little, just right.
Got it. What other problems can come up?
Well, sometimes the condenser doesn't cool properly.
What causes that?
It could be a problem with the seawater flow,
Okay.
like maybe the pump isn't working right or the strainer is clogged,
Okay.
or it could be that the condenser tubes are dirty, or the seawater itself is just too warm.
So the refrigerant can't condense properly.
Exactly.
What else?
The filter at the inlet of the expansion valve can get clogged.
The filter?
Yeah.
Okay.
And that can starve the evaporator of refrigerant.
Okay.
You might see high condenser pressure or icing at the valve.
Icing.
Yeah, because the refrigerator is expanding too much and getting too cold.
Makes sense.